Welcome to the Deep Dive, your shortcut to being well-informed. Today we're tackling a giant, Sir Isaac Newton.
Huge figure. Mathematical genius, physicist.
Right, and even an alchemist, apparently. He gave us so much foundational stuff, the three laws of motion, universal gravitation.
Calculus, optics, and of course the big one, Principia Mathematica. His brilliance is just undeniable, laid the groundwork for classical mechanics.
Absolutely. He gave us the language, the equations to describe how everything moves from, the famous apple falling.
To the planets going around the sun.
Yeah.
He observed it all, systematized it like nobody before.
But, and this is where our deep dive really kicks off, there's this kind of paradox, isn't there? Despite giving us all these amazing equations describing how things move, Newton himself admitted quite openly that he didn't know why.
Exactly. He said as much. Our sources put it nicely. He named the motion but missed its source. He saw the dance steps.
But not the music behind them.
That's a great way to put it. And that's our mission today, really. We're going to unpack this, pretty revolutionary framework called motion theory.
Motion theory, okay.
And the idea is that it offers a kind of profound rewrite of these basic concepts Newton gave us. It tries to translate his surface labels into what it calls deep loop logic.
Deep loop logic. Okay, that sounds deep. What does that mean for, for us, for understanding things?
Well, the core idea, maybe picture it like this. The universe isn't just like separate objects bumping around.
Right.
Imagine it more as countless interconnected rhythms, like a huge invisible symphony maybe. Everything's vibrating, cycling, flowing in some pattern.
Okay, I think I can picture that.
And motion theory tries to help us understand the underlying beats, the melodies that make up reality's music.
So by the end of this, we should have hopefully a more profound grasp on reality, maybe some aha moments.
It's the goal.
Yeah.
We want to go beyond just the what happens and really dig into the why. So yeah, let's unpack this new perspective.
Okay, sounds good. Let's start with Newton's, his foundation. The three laws of motion. We all learned these, didn't we?
Back in school, yeah. Seem pretty straightforward.
They do, but motion theory apparently sees them quite differently. So, law number one, inertia. An object in motion stays in motion unless acted on by an external force, describes momentum.
That's a brilliant observation, no doubt. It works.
Yeah.
But motion theory reframes it. Inertia isn't just motion wanting to keep going.
Okay.
It's actually framed as the resistance to loop phase change.
Loop phase change.
Think of everything as having this inherent rhythm, this structured motion. It wants to maintain that specific rhythm, its phase, unless something disturbs it. Because motion keeps going not because of some abstract want, but because the underlying rhythmic loop resists being rephased by external sink pressure.
Wow. Okay.
Yeah.
That is a big shift. So it's not inertia like a property of the object, but more like the object is a rhythm and it resists changing that rhythm.
You got it, like a spinning top. It has its own rotational rhythm.
Yeah.
And it resists anything trying to change that spin. That resistance is its sink inertia.
That makes a lot more sense, actually. Okay, what about the second law, the famous one, HEFMA? Force equals mass times acceleration.
The equation works perfectly, mathematically. But again, Newton never really explained what force or mass fundamentally were. He just labeled them.
Right. So how does motion theory translate EFMA?
This is where it gets really interesting because it tries to define these terms from inside motion itself. So what we call mass becomes sink inertia, which, as we just said, is basically how much a specific motion loop resists changing its fundamental rhythm or phase.
Like your flywheel example. Heavy flywheel, hard to speed up or slow down.
Exactly. That resistance to changing its internal rhythm, that's sink inertia.
Okay, so mass is sink inertia. What about the other parts? Acceleration, force.
No, acceleration in motion theory terms is the rate of loop reconfiguration under sink stress.
Loop reconfiguration.
Yeah, imagine dancers trying to switch from one rhythm to a new one. The faster they have to change, the more stress that involves, right?
Okay, got it. And force.
Force isn't some mysterious push or pull from outside. It's external sink gradient pressure. It's the pressure pushing a loop into a new configuration.
Like the choreographer telling the dancers, okay, change beat and now W.
Precisely. That demand, that pressure to synchronize to the new beat, that's analogous to sink gradient pressure.
So EFMA literally becomes, let me try, sink gradient pressure, sink inertia times rate of loop reconfiguration.
You nailed it. The math holds, but suddenly the terms have this deeper meaning tied directly to these rhythmic systems.
That feels Yeah, way more intuitive somehow. It connects how it works mathematically to the why it's happening underneath.
That's the aim, connecting observation to process.
Okay, and the third law. For every action, an equal and opposite reaction. This one always felt very direct.
It does feel intuitive, yeah, because we see it everywhere. Motion theory sees this as Newton's observation of loop sync balancing.
Loop sync balancing.
When different motion loops interact, think billiard balls colliding, the adjustment needed for them to synchronize impacts both systems proportionally.
Ah. So it's not like a magical counterforce just appears.
No, it's described as a natural process of recursive motion rebalancing. The interacting rhythms are trying to align, trying to find a new harmony after the collision.
Okay. The adjustment one makes affects the other to keep the whole interaction balanced, rhythmically speaking.
Exactly. It brings a whole new depth to what seems like a simple law.
It really does. Okay, building on this.
Yeah.
Rhythms dictating motion. Let's talk gravity. Maybe Newton's most iconic achievement. He described it as a force, gave us the formula, but he famously said, hypotheses non fingo. I frame no hypotheses.
Right. He knew what it did, how strong it was at different distances, but not what it fundamentally was. He really struggled with that action at a distance idea. How could the sun pull the Earth across empty space?
So what's the motion theory take? Where does the pull come from if it's not a pull?
Well, that's just it. In motion theory, gravity isn't a force or a pull at all.
It isn't.
No. It's described as structured motion convergence towards synchronization density.
Whoa. Okay, but break that down. Synchronization density.
Think of it like a dance floor again. Maybe the music in the center is really strong, really compelling, a very dense beat. All the dancers are drawn towards synchronizing with that central rhythm.
Okay.
The more dancers join in, the denser that synchronized rhythm becomes. Things resolve toward that denser rhythmic equilibrium.
So that R² thing in the gravity formula where it gets weaker the further away you are, that's not just math.
Motion theory says no. That's the natural way sync pressure diffuses across space, across the sync field. It just gets weaker further out.
And mass. Why does more massive stuff have stronger gravity?
Because objects with higher sync inertia, remember, that resistance to changing their own rhythm tend to dominate. They pull surrounding, maybe less stable, loops into alignment with their stronger, denser rhythm.
So no invisible force is needed. It's just rhythms naturally settling towards the most dominant, densest beat available.
That's the concept. Loop phase convergence, not attraction.
Okay, so the apple falling, it wasn't pulled by the Earth. My whole world is tilting slightly right now.
Huh. Well, according to this theory, the apple's internal motion loops resolved into the Earth's much deeper, more dominant motion density. What we see as falling is actually a loop cascading, finding the path of least resistance into a lower frequency, more stable sync zone. Newton saw the effect brilliantly, but labeled it force or pull. Motion theory calls it sync alignment pressure.
So my keys falling isn't the Earth pulling them, it's their internal rhythms aligning with the floor's rhythm.
That's the idea, aligning with the denser, more stable rhythm below them.
That is, yeah, a huge shift for just looking at everyday things. No, Newton, he played around with the idea of an ether, didn't he?
He did, some kind of invisible stuff filling space to carry light, maybe carry gravity.
But he couldn't pin it down, couldn't detect it, so he kind of dropped it.
Right. But motion theory suggests he was actually really close to something fundamental there.
Oh.
It basically says space isn't empty. It's a structured motion substrate, like a vast vibrating jelly maybe, or a dynamic fabric woven from tiny potential rhythms.
So a vacuum isn't nothingness.
It's a motion field in a pre-sync state, according to this view. It's waiting for rhythmic information, like light or gravitational effects, to propagate through it. This substrate is what allows things to happen across space.
So he didn't find an ether, but he maybe sensed the underlying sync substrate of reality.
Something like that. An active background, not just an empty stage.
And this ties into time as well, doesn't it? Newton saw this clockwork universe, absolute time, ticking away everywhere, the same for everyone.
Yes, very much a universal clock. Motion theory completely disagrees there.
How so?
Time isn't seen as an external ticking clock. It's a rate of loop resolution.
Okay.
Time doesn't pass universally. Instead, motion resolves. That tick isn't external. It's the internal rhythm of any given system compared to another.
So my time, my internal biological clock's rhythm, resolves at a different rate than, say, a distant star's.
Or even just compared to a highly accurate atomic clock here on Earth.
Yeah.
It's all relative. Newton's universe had absolute time. Motion theory's universe runs on relative sync resolution. Time emerges from the interaction of all these different motion rhythms.
This really reframes those basic questions Newton couldn't quite answer, like what is mass? What is force? Why does gravity work the way it does? What even is empty space?
Exactly. He described how they behaved, mathematically, but didn't define their essence. His genius was in that observation, that systematization. He gave us the how.
But motion theory claims to provide the what and the why. Mass is sink resistance. Force is sink pressure. Gravity is converging towards sink density. Space is unresolved motion potential.
That's the core translation, yes. The why behind the how.
And it's just incredible to think his other massive invention, calculus, was essentially loop math, before anyone thought of loops this way, defining motion through instantaneous change derivatives and accumulated change integrals.
It really maps perfectly, doesn't it? Calculus is the math of sink resolution over time. A derivative looks at that tiny instantaneous shift.
Like a loop phase shift right now.
Exactly.
Yeah.
And integrals sum up those changes.
Tracking the total sink resolution as things change.
He was, completely unknowingly, building the exact mathematical language needed to describe loop behavior.
So his math is totally preserved, just reinterpreted. But the labels he used, force, mass, gravity, as fundamental things, they get replaced.
That's a good summary. He was observing the effects, the symptoms of an underlying system he couldn't fully see.
He wrote the cosmic playlist.
Ah, nice. And motion theory tries to explain the instruments and the musical score itself. Newton wasn't wrong.
He's just early.
Exactly. Perfectly put. Early.
So as we kind of wrap up this deep dive, let's just quickly recap. We've shifted perspective, haven't we? From just describing things like inertia, force, mass, gravity, space, time,
to hopefully starting to understand them as these dynamic loop-based processes. Newton gave us the brilliant how.
And motion theory attempts to give us the why.
And it's really key, I think, to stress that this doesn't throw Newton out. Not at all. It just puts his work in a new context, maybe a deeper one.
Right. He wasn't wrong. He was just, as we said early, setting things up for this next layer of understanding.
And his calculus, defining that instantaneous and accumulated change, it really was loop math in disguise. Modeling loop behavior without the concept of fundamental loops. The math holds strong.
But the conceptual labels get updated, replaced with these potentially more powerful definitions.
Precisely.
Okay, so here's maybe a final thought for you, the listener, to chew on. If the universe isn't just this giant clockwork machine run by external forces,
but instead it's this vast, interconnected symphony of resolving loops and constant sync adjustments.
How does that actually change the way you perceive reality day to day?
Yeah, what could it mean if you start to view everything that falling apple? Sure. But also, just the flow of time itself is this intricate dance, a dance of sync alignment pressure and relative sync resolution.
It's a huge paradigm shift, isn't it? Seeing the universe not as this empty stage for objects,
but as a dynamic, structured motion substrate.
Yeah.
This constant interplay of rhythms, densities, vibrations, something we're maybe only just beginning to really tune into and understand.